Okay, our next speaker, Beau Webber, APL for the researcher.
Hi.
Over to you.
Thanks. Well, as I said in my introduction, for a scientist, APL is a wonderful tool. You can go in the lab with no idea what you... Well, you may go to the lab with an idea of what you're going to do, but the data may not agree with you. You may have something completely different to do when you actually come down to it. APL gives one the ability to handle large multi-dimensional arrays and interact with it in a totally free manner, but also then incorporate those into tools that you can use again and again and give to other people. One of the main things I do with it is measure pore size distributions. I use APL for it. Moving it over from the back, running the problem. I work mostly in academia, but also do some industrial measurements as well, pore size distributions. I do both the science of nanoscience, the study of liquids and pores, the nanostructure of liquids and pores, and I turn that around and apply that to metrology. And here's a typical graph where one can see APL being used in a number of places, the data capture, the preliminary analysis, the calibration of what is now a normalized graph where the melting point distribution is measured in known units. You can see simple straight lines fitted to the data by just defining linear regions on the x-axis, and then it finds straight line fits, solves those equations to generate intersection points, calculates the median, all very straightforward, but it's a straightforward way of getting sample filling factor, bulk melting point, and melting point depression, which is a way of measuring pore sizes. These graphs are calculated in APL. We were using a script I wrote a long time ago. We've lost the angstrom since that's one of the things I'm going to demonstrate for fonts as well. Somehow we seem to have lost it on this particular graph. From that we can calculate a pore size distribution. These graphs are output as postscript directly from the APL, and I can show you them if we just dropping out and go into the web page. You can see these automatically translated to SVG on the web page. Not using all the new tools built into micro APL. There's an SVG graph that we can pick up and pan and zoom into if we want. Okay. Particularly notice the width of this distribution as well as its height and pore size. We'll be coming back to that as it's an important point in a later graph. So, APL, concise, elegant, manipulates, holds array data. One of the nice things is one can hold a whole algorithm in one's head. Very early on, when I was using APL, I'd been to a conference, I'd heard about this back projection algorithm for reconstructing images. It's still used in X-ray CAT scanners. I was able to write this, hold it in my head, sitting in the back seat of the car on the way back from the conference, jot it down on the back of an envelope at a convenient thing. One of the earliest routines still on my machine from the early 70s. This is what it does to a unit matrix. This is the operation it performs on a unit matrix. So very simple, very straightforward. Still readable in APLX from a workspace back in. Well, in fact, this dates from before the APL existed. It was actually translated from a workspace on a VAX 750 in APL 11. Nowadays, the most common way of doing this with NMR is the fast Fourier transform. I'm just bringing this up as a very common algorithm used, implemented in many different languages and many different forms. The crucial point of a fast Fourier transform is you can reduce everything to a 2x2 complex operation called the FFT butterfly. And the really nice thing as an APL is that here's an algorithm from the 1973 APL Congress. You start by restructuring the data as a 2x2 by as many 2s as you need to hold it all. And so it is a very clear implementation of the fast Fourier transform butterfly and the operations you perform on it. This code would be a lot more concise if this APLX understood complex variables. But even so, we create our sine and cosine tables in a few lines, scaling them to fit the data. Most often you buy a 1,000-point Fourier transform, 1,024-point Fourier transform, and you have to run a different routine if it's a 10,000-point Fourier transform. And these two lines actually perform the Fourier transform. So it's a very concise way of representing high semantic density, you might say. And that sort of thing encourages rapid agile development. Here's a typical NMR system doing imaging work in the laboratory in a high field magnet at low temperature, at variable temperature, the nitrogen viewer here. And here's an example of measuring. We just saw the graph of measuring pore size. Here's applying the fast Fourier transform to measure data to actually achieve a 2D map of pore size distribution. So this isn't image, just a simple image. It's an actual image of pore size distributions. And here is just a piece of code that actually did this TypeScript map. So the other feature that APL is increasingly gaining is multitasking. It's an essential tool when dealing with multiple things happening in the laboratory. And one of the first things that I found necessary to add to APL 11 was the ability to access Julian time in seconds, where the pod timestamp was actually too tricky when your measuring event might go over a leap year or an end of a month of an unknown. You have to work out how long a month is to calculate. Is this 1 second later or a day later? Quite tricky. Quad timestamp is not as convenient as Julian times. You can do Julian time in days and hours and seconds, and you'll see some graphs probably later where Julian time is actually displayed in hours. 0 to 24, each day is a new graph. They're fairly convenient for logging data in the lab. But the first multitasking construct I added was pipe to APL. I added this to APL 11. You have an APL expression. You have APL data. You have a Unix pipeline of Unix operations, Unix command line, and the pipe symbol. You apply the right-hand data, and if data comes out of the left, the area, you have more data piped back into APL after being through the Unix shell. And here's an example of data that's going out, but not coming back in, it's ending up on the printer. And here you've got data coming in, where you're listing the contents of a few directories, you might sort them to various things, and bring them back into APL. lot of facilities built into modern APLs to do those two examples, but any arbitrary new operation you want to do, if you're in a Unix environment, it might be a very convenient way to do it. And of course, even on PCs now, you've got single and I'm calling TC shell all the time. Not quite so often since APLX added the ability to do generalized expression parsing, borrowed from regular expression parsing, which is something I use heavily. So that was written up in quad. Later, not yet written up, is something I put that both into APL 11 and APLC. Something I put into APLC was formed, which is where you can hang pipes to external processes, where the two or more processes can run in parallel. So you can have Unix processes running in parallel with the APL, and the two are talking to each other. And you can do this. You can do this on a PC. Probably implemented fairly easily using the .NET calls now. And I used this to build an early GUI tool. One of the places other types of experiments I do are neutron scattering. The neutron beams coming along the collimator here, hits a sample, sprays out onto a meter square detector inside this 22-liter vacuum tank. I love this instrument. Precision of sub-millimeters, and the thing is the size of a railway engine and it has carriages, you know. This is the sort of image you get on the detector plate, and I've incorporated that into my lab tool's logo. Here's a GUI that I wrote using TCL. That's this panel here. The output is all in PostScript, which you could either, at the time I was using GB to view it. I now just, XV, I now use GB. This is the table, this is the map we've just seen. That is these parameters are accessed, which are in the raw data file. All this comes is directly read off the data file from either the machine at ILL or from his local machine. And this is a pre-designed PostScript form, which is filled in using Stream Editor with the actual parameters from the data, and then rendered on either the screen or sent to the printer. And this data is processed to produce what's called a radar distribution function. The intensity of the scattering is a function of X. Sorry, not the radar distribution. This is the scatter. This is the IFQ, the intensity of the scattering, as a function of inverse angstroms. Here we have an interpreter written inside a compiler. You can type your debug commands here. You can click on various buttons here to achieve the same effect, and you can ask for various help pages. The commands go into a buffer here, because sometimes you'll actually end up waiting for data to come with the issue of the command. The data hasn't yet arrived. The commands back up there, you can see what's actually still waiting. The commands are being processed. It's important to know what's been done, are listed in this window, and the actual data that's being processed gets logged in that window. This is an example of a domain-specific language. It has nouns, it has verbs. Here's the sort of simple bit of APLC code to handle the verbs. And here's an example of a noun table being read in and interpreted, read into APL from an external file. Here's a command table. Command tables can chain in new command tables, so the thing is fairly controllable. And the nice thing about doing it this way is you can start the program running and you can write command files and data variables externally, and when it gets to them, it will access them and run them, or you can challenge to do a particular one without This is an example of the data out measured on 2 or 3 machines at various detector distances. Here's the actual measured data, wide range of intensities. You can see some of the joinings, others are pretty invisible. This data also is actually fitted with a piecewise polynomial that follows all the peaks and wiggles. You need to do that because the raw data is all on different length scales depending on what detectors you've used. I want to do a Fourier transform, I have to have equal space data for a fast Fourier transform. So that this ends up as a 100,000 point Fourier transform, and I end up with, I end up with data with the later on. This is other data from another type of sample. This type of sample is structured, so we get peaks in it. And to do all the corrections, here's a graph that's been actually drawn by Paul with the previous graph draw to record recursively with an object-oriented pre-package, and the different events arranged. There's a number of functions like these that you have to implement to do the geometry. Very simple to do in APL. And here you can see the result from the left-hand graph of the previous case. Fairly smooth data. The red data is the measured data. And the really interesting thing is that we can actually calculate the scattering from models of pores that in the regular case would look like this: spherical pores on the hexagonal lattice, with spaces where the pores intersect with each other, so you can see through the lattice is porous. And we can actually calculate the scattering from such a lattice, and that's the green lines that go through this data. Now that's not a fast calculation. I did it in APL. I did it in APL because I wanted to be able to believe the result when I finished. And APL, you have correctness by inspection. A few lines, those few lines of code there, sum up the core of the algorithm, excluding reading in files, saving data files and things like that. And it's implementing this multi-dimensional integral here with a multi-column integration. I'm sure it'll be efficient, more efficient in other languages. That I don't care, because I could run it for a month in another language, and I wouldn't believe it. I wouldn't know whether the result was good. In APL, I can inspect the equations. I know the data's right. I can do additional tests on the data to prove it's right. And to me, the real thing is the testing by inspection. And this is the sort of data you get out. A radial distribution function for this sort of data here. One applies the Fourier transform to it again. This is just the Fourier transform with a wraparound to make it physicist Fourier transform rather than engineers. For the neutron scattering transform, you multiply it by R first, and you divide it by Q afterwards. So not surprising, the small q you get quite a noise. That's the measured data, and that's the calculated data fitted to it. Now, we've got the width wrong. Why? Well, actually, it's not the calculation that's wrong. It's the width there has come from the NMR parametrometry experiment you saw earlier. I put that into the simulation. That width is actually slightly under what it should be. More or less right. Why do the two disagree? Well, it's the actual data that's wrong. The collimator that feeds that there's also a velocity selector there, which is a 10% width. And so that's actually blurring that data. The measured data can actually blur. If we blur our calculated data with a simple triangular APL expression, we get something much closer. And what that's telling us, as I say, I've got a calculation running at the moment, which is broadening that by another 20%. It's adding another 20% variance to that pore diagram we saw of the ideal lattice, perfectly regular lattice. So that's one of the things I do. One can do other GUIs very simply in APLX now. That's a number that just live on my desktop. Some of them are fairly trivial, but they are GUIs they work with, they operate on. This one, you feed this, you highlight a postcode, you copy it into pasteboard, paste it into clipboard, you hit this icon, and what the contents is replaced by an HTML expression which gives you a multi-number, which you can paste back into your document. Simple things like that. Others are far more complicated. They're easy to build once you get a working thing in APLX. You just save it and you select .exe instead. And you've got it. That doesn't build you a GUI, but that does build you an executable. And some of these are mostly GUIs. Here's a very simple one. I can't demonstrate it running because I did this for somebody. I don't have the hardware, but it measures power particle density. There's boxes you can check parameters in, buttons you can hit, drop-down menus you can change the parameters that you change. Here's a GUI that I can. How am I doing for time?
You're fine.
Okay, I'll risk trying to run this one. Here's a GUI. A student was working on some neutron scattering data. I've built some simple GUIs to do to assist you to work with data back in the Atari days. They were so slow that the menus took minutes to drop. This is a more recent, very high-speed tape just to get her off the ground to do simple things that she needed for this experiment. Let's see if I can get that up. I've deliberately left the command window, the status window just there so we can see it. But here's our drop-down menus. We can put a neutron scatter all scattering, so it all seems to provide those data as run numbers, which there's a taxa suffix onto it, a taxa prefix as well. We can read that data in. And we get some neutron scattering data. That's liquid, but it's liquid in pores. How do I know some pores? Well, there's a small angle scatter there. This is a diffraction experiment. We're seeing the tail of a small angle scattering from the same sort of graph we saw previously from D22. The first thing, if we're interested in diffraction, we want to get rid of that small angle scattering thing. So we'll ask you to fit a q to the minus 4th peak, which will fit that fairly well. The complexity is not the polynomial q to the minus 4th. It's actually, it is recognizing, doing a lot of other things to recognize the, you see this data doesn't go to 0, there's a beam stop, so we don't fly the detector. It's recognizing this minimum here, and it's applying a q to the minus 4th fit to that data. We can copy that data there, and the sort of simple thing you can do is do a left and minus right. Oh, sorry, I should have read that data back in. I need to read that data back in. And now if I go left minus right, I get this q to the 4th data. So the simple things like that. But more importantly is the q to the 4th parameters are registered up there. Slightly more complicated one. We want to read some more data in. This time it's going to be ice. It's got hexagonal ice peaks in it, a little bit of a q to the 4th tail, so we'll start by removing that, nice and flat. We'll do a fit to. We want to fit the baseline. Before we fit the peaks, we've got to know what the baseline is. And there's some broad peaks, there's some narrow, there's a lot of sharp peaks. I would normally do this more carefully and fit in some more intermediate ones. This is the sort of thing where APL really excels. The interactive control is very difficult to fit that base, to decide automatically what that baseline is. What I'm defining is short sections between which I'm going to do I'm going to join all those to get short sections together and do a polynomial fit through them. And now what I can do is remove the fitted baseline. That's now sitting on 0. And I can go back to another fit and do a generalized least squares Gaussian fit. I can do either individual peaks or automatic peaks, and that's doing a reasonable job of finding the peaks and listing the parameters in the table there. which there's a menu option to save. So, and there's about things that help things as well and so on. So it's a nice tool to run. APLX offers some nice facilities. Go back to the PowerPoint. Here's a much more complicated instrument. It's an NMR 1D dimensional imager. Again, a front panel with all the various things. The hardware has got some of it's implemented in VLSI for the RF manipulation. The IF intermediate frequencies is done in the gate array. Basically, an earlier version of that one. The low frequency audio frequency manipulation is done in APL, and the general program and control data communication is done to the box over the USB from inside APL using a module like that. There's the block diagram of the RS section. That's the IF section. You'll notice a set of the USB registers over on the right here. USB registers the load data into the things. USB data is to read and write to read the final data out of the thing and the status. That's the software that's written in APL. Everything you've seen up to now is on the left there, talking to USB registers, complex demodulator written in APL, various other things, the plotting, step and motion control for that system, and so on. Here's a more recent machine that I thought of bringing, but it's still in the prototype stage. It's a pulse NMR machine. Again, basically the same structure. A similar GUI is still being worked on. We've got a status window. We've got a command window that you can use to very useful in the development stages. Certainly to test things that aren't fully written into the GUI. Again, interface by this chip there. There's the module that I just held up. How am I doing for time now? 5 minutes. I could, if you want to see later, I can talk to that GUI from the APL, but I won't wait to load that up and everything. I'll move on. The sort of thing I'm working on at the moment, I've been working on, is one of the things you need for NMR pulse program, is the NMR spectrometer, is a pulse program, pulse sequencer, and there are a number of predefined pulse sequences that you need to create, and you want to give the user ability to create their own pulse sequences. So from a list of delays, named delays, and channels that you want the output you want to control, you run this APL function which creates this table using APLX. It's a general array editor, and what this sequence is defined by an initial state for all the items, values which last for one time slot, and transitions which cause transitions in the default state. This is the structure that I decided was the most easiest way to write a pulse program. And after a bit more translation, you end up with something. I don't know if you can you see the white letters there from the back? Maybe you might be able to see them. But this has now populated that previous block by sort of passing the default values down, 1, 1, 1, 1, the transition of the default thing, transition to the default value, the default value is now 0, puts it back to 1. It's evaluated the times. These times are all given in, these are APL expressions, but the times are not just values, they also contain a unit, maybe microseconds, maybe milliseconds, and maybe seconds, and these have now been evaluated into seconds, and this data is then sent over the USB to a stack-based sequencer in the gate array. You get data back. One of the most interesting bits of work I've done lately was to show that ice, which normally has a very fast 10 microseconds realization time, in these materials, near a silicon wall, has a much longer, can gain a much longer realization time. Here's the signal decaying, the NMR signal decaying is a function of time. And the sort of thing you would use APL, that's, if you melt all this, you get a water signal. So the first thing to do is to extrapolate that polynomial, extrapolate that back to 0. That tells you how much water you've got. That's how it tells you how much signal you should have at 0 time. This other signal here is recovery from the kilovolt pulse, RF pulse. This is microvolts of signal, looking at our following kilovolt of RF. Do an exponential fit to this section of the data. That's our long-term 100 microsecond decay, and do a Gaussian fit to what's left over. Very easy to do in APL. But the next thing is, in fact, you actually want to apply it to a whole pile of data at different temperatures, and I've got a routine that will run through those, if necessary, using the previous value as the best guess to start with it for the next thing. And that's the sort of data you get out, where you get temperature, you get data as a function of temperature, and that tells you the dynamics, how the dynamics are changing as in the water ice system. Very recently, there's a lot of interest in oil and getting oil out of carbonate rocks. The oil in sandstone rocks is nearly all used up. They want to get the oil out of carbonate rocks. So I've just been in a lab, and this is some very preliminary data where, yes, there's a long component, yes, there's a short component, both exponential, and that data is now fitted on. There's the data you saw before. This is relaxation at an air interface. There's oil, and that data I think turns out, you just see, turns out that we have an oil component already in the rock and a relaxation component like that. That is still being identified. But it's probably the unfrozen water in the system. This is an example of APL development on the fly. I'm moving from an old system to a new system. I am measuring every day in the lab. I don't want to stop the measurements running, so I just add another parallel process. I just start another APL window. I'm now up to 8. They just sit in a list here. They're you can see the code back there. They're all doing a simple operation. This one's reading in data from the old lab data connection point. This one's doing temperature wraps. This one's doing the temperature control. This one's doing that graph there, which is measuring room temperature, sample temperature, probe temperature, various other things. And down to this one, which actually sends the data, makes the data available over the network. And I was hoping to show you, this is an example of the melting curve, like I saw you slowly right at the beginning, and I was hoping to be able to show you that actually measuring from here over the network during the talk. Unfortunately, a brand new £1,000 worth of temperature reference box died a couple of weeks ago, and it's still away for repair. But I'm running out of time, I think.
Got a couple of minutes.
I'll leave it. I'd have to log in again. I've lost my login, so I won't do it. But yesterday quite successfully logged into the lab, got the latest data file, which was empty, and I could show you a similar data file, just graph that's already been down, that I can get down the network from a previous day's measurement. That is now it's a very convenient thing. I can sit at home and just make sure the data, there's no problem with the experiment, but at the time I had some problems with this particular new machine is hanging, and it turned out to be a USB drive that I'd missed the latest update on, so it put marks on it. Plug that in and it's been totally reliable again. So it was useful, that time, particularly to watch it, to make sure I didn't have to go and restart the measurement. Where next? As well as just using the hardware, just APL talking to the APLX, talking to the hardware for purposes of controlling and experimenting the data back, there's the option of actually putting APL into the gate array. It's now possible to actually program these gate arrays so that part of them are a general purpose processor. We can run C code. And given a C code, APL to C code translator like APLC, there's nothing to stop you uploading bits of APL right into the experiment that you're running, either so that you don't have to download the data, or in some cases, because you've got hardware multipliers on. Some algorithms may run very efficiently. As well as all these components, you can get hardware multipliers on some of these things. You can put the bigger chips, you can put multiple processors. And one of the really nice things is you can identify a bit of your C code that you want to run really fast and get any arbitrary bit of C code. And you can run it through one of their translators, and it will generate custom logic just to speed up that particular expression. And I see a lot of future for that. Going back right to that original quote-unquote paper on pipe, and I now see this really does need support, it's more general than use support as well. There's nothing to stop you having multiple processes in standard parallel processes there, a pipeline of processes right down here. Here I visualize just APL expressions talking to things you can see. But now that you have support, any of these boxes can contain an APL expression. Here we've got a systolic loop. It's one of the things that's been forgotten with multiprocessing. Very often you have to arrange your processors in a data pattern that suits your problem. Here we have a FIFO, segregation from this point here to this point here, named pipe. And what I see in the future is that APL can be hitched into sort of harness communicating processes and processors to actually take us into the next stage of speeding up computing. Thank you very much.
Any questions?
Well.
How many of your students are interested in APL as a result of seeing what you accomplished?
I did quite a bit with a few years ago with two students in the lab, and I had a continual throughput of students who went away into industry talking APL. Recently, I've got 3 students that want to work with me, and I've got no funds to fund them at the moment. So I shouldn't be here. I should be writing the next grant application.
I hope you make this presentation to non-APL groups.
I don't make it quite so clear that I think I'm going to start making it clearer that I'm using APL. The data is data that I've shown with people often. I've shown talks in America and various places. I don't make it quite so clear. This is my first time I've actually put it all together, where APL has been the feature. And I think I must pull APL more explicitly into the...
Make your peers jealous of your productivity.
They wonder how I do it.
Don't keep it a secret.
Richard, Simon, you need complex numbers.
You need a question.
I need a question.
What was the question? Do you need complex numbers?
That's
amazing. That's exactly.
I can't, The main guy, I know one guy I would love to sell APL to. I've never, I tell him I use it, I show him what I do with it. I've never bothered to tell him because he thinks complex. He thinks, APLC now has got on to quaternions and octonions. So if you want to know, if you want pointers as a good way, a good look, have a word with Sam Serban, who does the APL frequency asked questions page.
Okay, thank you very much indeed.
Cheers.